So the last part of 3.1 with limits, we're going to be looking at limits as not as they approach an actual x value. We are going to be looking at the end behavior, which is as x goes to infinity, which would be the far right of the graph, and as x goes to negative infinity, which would be to the far left of the graph. That's what we're looking for. So the key step is this very first property. If you can rewrite anything inside the problem with a 1 over x to the n, 1 over x to the third, 1 over x to the 20th, it's 0 for either limit, because as you approach 1 over x, it will always approach that piece where it approaches 0. Basically, the fraction gets bigger and bigger and bigger. Think about it. The denominator gets bigger and bigger and bigger, which makes the fraction become smaller. So that's what we're going to use when we do these problems. Anytime we start off with a piece that we have a fraction in it, we're going to have to simplify to use this. So we're going to look at some rules here. Think about it. If we have a constant function as I go to infinity, which means as I go to the right, it's always the constant, so it's always equal to 3. If I have a polynomial function, which means there are no jumps or breaks in my graph when I have that, okay, this will depend. You actually can look at the graph, or some of you can actually reason it out as I plug in a bigger and bigger number, what is going to happen. But it's super easy to do that incorrect in your head, so just sketch it out. So for this first one, if I were to sketch this inside piece, this fourth root polynomial, sorry, fourth power, it actually has a behavior now. It has some little squigglies in there. But remember here, I'm looking at, as I go on the right-hand side, positive infinity, which is going down. So my limit goes to a negative infinity. As I draw the negative 2x cubed plus 9, which is my cubic, which again is one of the shapes that actually you've done some in work in both in college algebra. It has this shape here. Again, you can put in your calculator to see that shape. So as I'm going to the left side, I'm going to a positive infinity. So for polynomials, I can graph them to look at the picture. With the next grouping, I'm going to start having pieces where I have a fraction. And this is really important. On the test, to get credit for these problems, you must show your work of getting it in the correct format, which means you have to get in the form of being able to use this property. So on this one, we're just rewriting it as 7 over x to the half power. That works. So we know by that property, anything with 1 over x to the n is going to approach 0. 0 times 7, 7 is just a constant, is 0. Now going to number 4 are the ones that y'all need to practice using this format. So look at the rule here. It says divide the numerator and denominator by x to the highest power in the denominator. Okay? Because we're wanting it to put it in the form of 1 over x. That's our goal. So I'll pull this over so that I can show out the steps. So my biggest exponent in the denominator is x to the fourth. So I'm going to take every single term and divide it by x to the fourth. And then I'm going to simplify. So that's a 1 over x. That's a 2 over x squared. This last term doesn't simplify. 1 minus 5 over x squared. So I've now simplified each piece. The rule says if I'm dealing with a limit as x approaches infinity or negative infinity, any one of those fractions, 1 over x to the n, will go to 0. So this goes to 0. This goes to 0. This goes to 0. This goes to 0. I end up with 0 over 1, which is 0. You must show your work for these. So going to number 2 on this one, my highest exponent in the denominator is x cubed. So I'm going to divide each term by the x cubed. Not over the whole piece, remember, it's over what's in the denominator. So x cubed by x cubed. This becomes x minus 5 over x, 1 minus 2 over x squared plus 1 over x cubed. Since I'm doing the limit, this goes to 0, goes to 0, goes to 0. Think about this. Now we need to look at what I'm doing. I'm going as x it goes to negative infinity. So right now, all of the rest of these that I crossed through are going to 0. So think about what x would do. As I plug in a smaller and smaller x value, negative 10, negative 20, negative 50, the x value means the y value is going to go down smaller as well. So my answer here is a negative infinity. So last one using this idea in this chart, we're dividing by x squared because that's in the denominator, highest exponent. It's not necessarily the first one, it's the highest exponent in the denominator. We're going to simplify, gives me 3 minus 7x squared, 4 plus 1 over x squared. Goes to 0, goes to 0. There's nothing to plug in this case or think about. So my answer here is 3/4. You will need to practice that type. If you are unsure, you can graph it and check it. But for a problem like number 4's 3 examples, I want to see your work. So we're going to do a few more real quick that are just like the ones we did. They're examples from the book just so you have some more examples using this rule. Remember, if you see a fraction when you're dealing with infinity or negative infinity limits, you need to divide by the highest exponent in the denominator. So here I'm going to divide by x. Eight plus 2 over x. 4 minus 5 over x. This now goes to 0. Answer is 8/4, which is 2. Same idea for number 50. We're going to start off. In this case, we're going to divide by the highest exponent, which is x squared. So x to the 4th over x squared, x cubed over x squared, 3x over x squared. Same thing in the denominator. Anything that's left that we can use the rule on, those go to 0. This one's a little trickier. You gotta again think about it. We're going to a positive infinity. So as I plug into x squared minus x, I know it's times 1/7, but the in behavior, think about a parabola. This is a parabola that would be facing up. So the in behavior on the right hand side, okay, would be a positive infinity. Think about that parabola. How do I know it's a parabola? Looking at this piece right here, x squared is a parabola. Going to number 54, I'm going to divide every term by x squared. Get a negative 5x minus 4 plus 8 over x squared. 6 plus 3 over x plus 2 over x squared. Using my rule, goes to 0, goes to 0. Again, stop and think about this. I do have a 6 in the denominator. That's going to just basically stretch or shrink it. So we say to ourselves, and if I'm going to write the idea down, I'm actually saying a negative 5/6x minus 4/6. What happens to that? I'm looking as I plug in a bigger and bigger x value. This is a linear line. It has a negative slope, so it's going down as I go to the right. I didn't even have to sketch that. As long as you know the definition of a slope with a negative slope is going to go down as a positive infinity as I'm going to the right, because that's what I'm looking for right here. So my answer here should be a negative infinity. 2 last examples. Again, anytime you need to pause, pause. But these 2 are ones that we just want to know the shape we should already know the shape. Okay. An exponential goes to the point 0, 1, and it has an asymptote here. So the limit as x goes to infinity gives me that arrow on the top, which is positive infinity. The limit as x goes to a negative infinity is over here, which is approaching 0. Look at the graph. My natural log still goes to this point 1, 0, has an asymptote. So now we look at this graph. As I approach from the positive 0 side, which is the right side, that's down here, because I'm going along this line, my answer should be negative infinity. Make sure you understand how to do all of the different parts.